There are seashells on the summit of Mount Everest. Not metaphorically, not as some poetic device, but literally, physically there. Marine fossils embedded in the limestone near the highest point on Earth, 29,032 feet above sea level. Ammonites, brachiopods, crinoids. Creatures that lived in a warm, shallow tropical sea hundreds of millions of years ago, now frozen into the rock at the roof of the world. And if you've never stopped to find that deeply strange, you should. Because those fossils are a message from a vanished world, a clue left behind by an ocean so vast, so ancient, so consequential, that its disappearance reshaped everything about the planet we live on. Its death built our highest mountains, created our greatest oil fields, triggered a global climate shift that eventually led to ice ages, and set in motion the evolutionary chain of events that produced us. The ocean's name is Tethys, and it is the most important body of water most people have never heard of. Before we continue, if you find yourself drawn to stories like this, to the deep hidden history written in rock and fossil and mountain, please subscribe to this channel. Your support makes it possible to keep exploring these questions. Thank you. So let's start with those fossils on Everest, because they are the perfect entry point into a mystery that took geologists the better part of 2 centuries to fully solve. When the first serious scientific expeditions reached the upper slopes of Everest in the early 20th century, they brought back rock samples. And when those samples were analyzed, the results were startling. The limestone near the summit, a rock type called the Comolangma Formation, was packed with the remains of marine organisms, creatures that had lived in seawater, on what is now the highest mountain on Earth. The question that immediately presents itself is obvious. How does seafloor end up at 29,000 feet? The answer requires understanding one of the most dramatic geological stories ever told. A story that begins not with mountains, but with their opposite, with a warm tropical ocean that once covered much of the space between what we now call Europe and Asia on one side, and Africa and India on the other. An ocean that was, at its greatest extent, wider than the modern Pacific. An ocean that existed for over 200 million years and then was consumed, plate by plate, kilometer by kilometer, until almost nothing remained. Almost. The man who first gave this lost ocean its name was an Austrian geologist named Edward Suess. In 1893, Suess was working on a monumental multi-volume synthesis of Earth's geological history, a work called The Face of the Earth, and he noticed something that others had overlooked. The fossil record across an enormous swath of the world, from southern Europe through the Middle East and into South and Southeast Asia, showed remarkable similarities. The same marine creatures, the same reef systems, the same sedimentary sequences appearing in rocks that were now separated by thousands of miles of land. Something had once connected all these places. Some vast body of water had once occupied the space where mountains and deserts and plateaus now stood. Suess named this vanished ocean Tethys, after the Greek sea goddess, daughter of Oceanus and Tethys, sister and wife of the Titan Oceanus, who encircled the ancient world. It was an appropriate choice, because the Tethys Sea had indeed encircled much of the ancient world. But here is the first twist in the story, the first place where the reality turns out to be stranger and more complex than the simple narrative. The Tethys was not one ocean, it was 3. 3 successive oceans, each born in roughly the same region of the globe, each shaped by the movement of continents, each living for tens of millions of years before being consumed by subduction or squeezed out of existence by collision. Geologists call them the Paleo-Tethys, the Tethys proper, and the Neo-Tethys, though the boundaries between them are gradational and the naming conventions have shifted over decades of research. The ocean that Suez identified from fossil evidence was primarily what we now call the Neo-Tethys, the youngest and best preserved of the three. But to understand it fully, you have to go back much further, to a time when the geography of Earth was so different from today's that it would be genuinely unrecognizable. Go back 300 million years to the late Carboniferous and early Permian periods. The world at this point is dominated by a single vast supercontinent, Pangaea, the assembly of nearly all Earth's landmasses into one continuous block of crust. Pangaea wasn't a neat, symmetrical landmass. It was roughly C-shaped or wedge-shaped, with a great embayment on its eastern side opening toward a global superocean called Panthalassa, meaning all seas, which covered most of the planet's surface. And within that embayment, caught between the northern portion of Pangaea, which geologists call Laurasia, and the southern portion, which they call Gondwana, was the Paleo-Tethys. An older ocean, already ancient by Carboniferous times, already being squeezed and consumed as the two halves of Pangaea pressed together. The Paleo-Tethys was dying even as Pangaea reached its maximum assembly. And as it died, something new was being born just to its south. A series of continental fragments, long ribbons of crust that had broken away from the northern margin of Gondwana, were drifting northward across the Paleo-Tethys, leaving in their wake a brand new ocean basin opening up between them and the Gondwana coastline. This new ocean was the Neo-Tethys, the ocean that would come to dominate the Mesozoic world, that would shape the Triassic and Jurassic and Cretaceous periods, that would be the dominant oceanic presence on Earth for 200 million years. Born from the breakup of Gondwana's margin, it opened like a zipper running from west to east, widening over millions of years as new seafloor formed at a spreading ridge in its center. Picture the Triassic world of 250 million years ago, just after the greatest mass extinction in Earth's history had reset the biosphere. The Tethys at this point is a broad, warm, wedge-shaped sea, open to the east where it connects to the Panthalassa superocean and narrowing to a point somewhere in the region of what is now Western Europe. It straddles the equator almost perfectly, this long east-west oriented basin receiving the full force of tropical solar heating year-round. The water is warm everywhere, extraordinarily warm by modern standards, surface temperatures possibly reaching 35 or even 40 degrees Celsius in shallow regions. There is no cold, deep water circulating up from polar regions, as there is in our modern oceans, because the poles themselves are relatively mild. This is a greenhouse world, CO2 levels several times higher than today, global temperatures perhaps 10 to 15 degrees warmer than our modern average. And the Tethys is both a product and a driver of that warmth. The Tethys in the Triassic was not yet the vast ocean it would become. It was more like a long, warm inland sea, something like a greatly enlarged Mediterranean, but already it was biologically extraordinary. The shallow margins teemed with life recovering from the end Permian extinction. New coral reef systems were being established, the ancestors of the complex reef ecosystems that would dominate Tethyan margins for the next 200 million years. The first ichthyosaurs were evolving in these waters, dolphin-like reptiles that would come to dominate Mesozoic seas. Nothosaurs patrolled the coastlines. Ammonites, those elegant coiled cephalopods, were diversifying explosively after nearly being wiped out at the Permian boundary. The Tethys was a cradle of recovery, a warm nursery for a recovering biosphere. And the world around it was changing rapidly. Pangaea was not stable. The forces that had assembled the supercontinent were already working to tear it apart. Hot spots in the mantle, rifts forming in the crust, the relentless engine of plate tectonics beginning to break the great landmass into the pieces that would eventually become our modern continents. The first major split came in the Triassic and early Jurassic, when what would become North America began separating from Africa and South America, opening the early Atlantic. This rifting had consequences for the Tethys, changing the circulation patterns, altering the connection between Tethys and the Western Ocean. But the major transformation came later, in the Jurassic and Cretaceous, when the Tethys reached its maximum development and its greatest influence on global climate and life. By the Jurassic period, 150 to 200 million years ago, the Tethys had expanded dramatically. Gondwana was breaking apart. Africa and South America were beginning their long separation. India had not yet fully detached from Gondwana, but was beginning to show the first signs of the independent journey that would define its geological history. And the Tethys was widening, deepening, becoming a true ocean rather than an inland sea. The spreading ridge at its center was generating new oceanic crust at a rapid rate, pushing the opposing continental margins apart, making room for an ever larger body of water. At its maximum extent, in the mid-Cretaceous around 100 million years ago, the Tethys Ocean was genuinely enormous. Stretch your mind to encompass this geography. It ran continuously from what is now the Atlantic coast of Spain and Morocco, across the region of the modern Mediterranean, through the Middle East, across what is now Iran and Afghanistan, through the Indian subcontinent, which was then an island far to the south, through Southeast Asia, and opened into the Pacific. The North Shore was the southern coast of Laurasia, roughly the position of modern southern Europe and Central Asia. The South Shore was the northern coast of Gondwana, the coast of Africa, Arabia, and the land masses that would become India. Between these shores stretched thousands of miles of warm tropical ocean, a body of water that in places exceeded 3,000 meters in depth, while in others spread as vast, shallow carbonate platforms barely deeper than a modern swimming pool. And this ocean was a machine, a planetary climate machine of extraordinary power. The warm Tethys waters drove a circulation system that had no modern equivalent. Because the Tethys straddled the equator and was oriented east-west, it allowed a warm equatorial current to flow continuously around the globe, from the Tethys into the Pacific and back. This Tethyan circumglobal circulation, as oceanographers call it, acted like a giant conveyor belt of heat, distributing warm tropical water across enormous distances, suppressing the temperature gradient between equator and poles, keeping the entire planet in a warm, equable state. The Mesozoic greenhouse climate, that long interval of warmth when dinosaurs thrived at high latitudes and there were no polar ice caps, was in significant part maintained by this Tethyan circulation system. Take away the Tethys, and the Mesozoic world looks very different. The ocean wasn't just a feature of the warm climate, it was one of its fundamental causes. The shallow margins of the Tethys were equally remarkable for what they produced: carbonate sediments, limestone, dolomite. The shallow, warm water, supersaturated with calcium carbonate, was a factory for reef-building organisms, for the accumulation of shell material, for the precipitation of carbonate minerals. Kilometre after kilometre of shallow Tethyan seafloor was being continuously buried under carbonate sediment, building up sequences hundreds of meters thick over millions of years. And today, those ancient Tethyan carbonates form some of the most recognizable geological features on Earth. The white limestone cliffs of the Alps, the Dolomites in northern Italy, named after the mineral dolomite that characterizes their rocks, the limestone plateaus of the Middle East, the carbonate sequences exposed in the Zagros mountains of Iran. All of these were once the floor of the Tethys Sea, built grain by grain in warm, shallow tropical water, then lifted thousands of meters into the air by the tectonic forces that closed the ocean. But the Tethys was not only producing limestone in its shallow margins. In its deeper basins, something else was happening, something that would have consequences reaching far beyond the geological record into the economic and political realities of the modern world. In the deeper parts of the Tethys, particularly in restricted basins where circulation was limited, the bottom waters became anoxic, depleted of oxygen. In these oxygen-free conditions, organic material that sank to the bottom, the remains of plankton and algae and other organisms, was not decomposed. Instead, it accumulated layer upon layer, mixing with fine sediment, building up into what geologists call source rocks, organic rich shales and mudstones packed with the incompletely decomposed remains of ancient life. Over millions of years, as these source rocks were buried deeper and deeper by overlying sediment, subjected to increasing heat and pressure, the organic material was transformed, cooked essentially by geothermal heat into hydrocarbons, petroleum, natural gas. And where conditions allowed, these hydrocarbons migrated upward through porous rock until they encountered an impermeable seal and accumulated in traps. The oil and gas fields of the Middle East, the greatest hydrocarbon reserves in the world, the fields of Saudi Arabia, Kuwait, Iraq, Iran, the fields of the Persian Gulf region that between them hold more than half of the world's proven oil reserves, these are the legacy of the Tethys Sea. Every barrel of oil pumped from the Persian Gulf is in a very real sense distilled ancient Tethys. The organic material of Tethyan plankton, transformed by time and heat, is what powers a significant fraction of the global economy. The lost ocean is literally fueling the modern world. This is perhaps the most startling single fact about the Tethys, and it deserves a moment of reflection. When you fill a gas tank, when you buy a plastic product, when you fly in an aircraft, when you benefit in any way from the hydrocarbon economy, you are in a sense drawing on the biological productivity of an ocean that ceased to exist 30 million years ago. The Tethys is not simply a curiosity of geological history. It is a direct material presence in contemporary life, invisible but pervasive, its ancient carbon now oxidized and rising into the atmosphere, changing the climate in ways that the ocean itself, in its living days, would have helped to moderate. There is something almost poetic about that, though perhaps not in a reassuring way. But we're getting ahead of ourselves. Let's return to the Cretaceous, 100 million years ago, the Tethys at its height. The ocean is vast, warm, biologically rich, climatically powerful. The continents are still in transit, still moving toward the positions we know today, but still far from them. Africa is separated from Europe and Asia by the full width of the Tethys. India is an island, an oceanic island, floating northward through the Tethys waters, thousands of miles from the Asian continent. The Atlantic is opening, young and narrow compared to today. The world is unrecognizable by modern standards, and yet the seeds of the modern world are all present, moving slowly toward their destined collisions. Because that is what is coming. The closing of the Tethys, the most consequential series of geological collisions in the last 200 million years of Earth's history. And it begins, like so many catastrophes, not with a bang, but with a slow, imperceptible approach that accelerates over millions of years into something genuinely transformative. The mechanism is subduction, the process by which oceanic crust, denser than continental crust, dives beneath the edge of a continent and sinks into the mantle, pulling the attached oceanic plate behind it and drawing the distant continental margin ever closer. The northern margin of the Tethys, the southern edge of Laurasia, had been consuming Tethyan oceanic crust for tens of millions of years already, a continuous process of subduction that maintained the size of the ocean even as new seafloor was being created at the spreading ridge. But as the spreading rate slowed and the subduction rate continued, the balance tipped. The ocean began shrinking, and the continental fragments on its southern side, Africa, Arabia, India, began their long approach towards the Asian continent. India's story is the most dramatic of these collisions, the one that would produce the most spectacular geological result, and it's worth dwelling on in some detail. At the end of the Cretaceous, 66 million years ago, India was still an island continent, separated from Asia by a significant width of Tethyan Ocean. But India was moving north at a speed that was extraordinary by plate tectonic standards, driven by a mantle plume beneath it and pulled by the subduction of the Tethyan plate at the Asian margin. The rate has been estimated at up to 15 centimeters per year, faster than fingernails grow, which doesn't sound impressive until you multiply it by millions of years. At 15 centimeters per year, India closed 3,000 kilometers of ocean in 20 million years. It was moving like a freight train in geological terms, and the Tethyan ocean floor was being consumed ahead of it at a rate that would have been, if you could have watched it on a time-lapse spanning millions of years, almost violent. The soft collision, the first contact between the leading edge of India and the southern margin of Asia, occurred approximately 50 million years ago in the Eocene epoch. But this was not a sudden event. The closing of an ocean between two continents is a process that unfolds over tens of millions of years. First, the ocean floor disappears, consumed by subduction. Then, the sediments that had accumulated on the ocean floor, the carbonates, the deep-sea clays, the organic rich muds, are scraped off the subducting plate and plastered against the edge of the overriding continent in what geologists call an accretionary prism. Then the continental margins themselves begin to converge, and the collision proper begins. Continental crust is too buoyant to subduct. It can't sink into the mantle the way oceanic crust does. So when two continents finally meet, they crumple. They fold. They thicken. They push up. The former ocean floor, those kilometers of limestone and shale and ophiolite that had accumulated over 200 million years, is squeezed between two converging continents and forced upward, lifted from the seafloor to altitudes that would have seemed physically impossible. And the result of that ongoing collision, still happening today, still pushing the Himalayas upward by millimeters per year, is the highest mountain range on Earth. The Himalayas are the tombstone of the Tethys. Every peak in that range, every summit that climbers spend years training to reach, is built from the material of a vanished ocean. The fossils on Everest are not anomalies. They are the expected consequence of an ocean floor being lifted 29,000 feet into the air. The Komolangma limestone that forms the summit of Everest was deposited in the Tethys Sea roughly 250 to 500 million years ago, when that rock was on the floor of a tropical ocean somewhere near the equator. The creatures whose remains are preserved in it had no way of knowing, obviously, that their sea floor would one day be the highest point on Earth. But in a very real sense, Everest is Tethys. The mountain is the ocean transformed. The Himalayan collision was not the only one. As the Tethys closed, similar collisions were happening along its entire length. Africa moved north and began pressing against southern Europe, closing the western end of the Tethys and producing the Alps, the Apennines, the Pyrenees, the mountains of the Balkans and Turkey. The Arabian Peninsula, which had been part of Africa, detached and moved independently, colliding with Asia and producing the Zagros Mountains of Iran, another range built entirely from former Tethyan seafloor. The complex mountain belts of Central Asia, the Caucasus, the mountains of Afghanistan and Pakistan and Turkey, all of these are products of the same process. The progressive closure of the Tethys from west to east over 50 million years, each collision zone marking a place where oceanic crust once existed, and now the compressed, folded, uplifted remnants of seafloor sediment stand as peaks and ridges. The entire alpine Himalayan mountain belt, the great chain of mountains that runs from Morocco to Southeast Asia, is essentially a suture, the scar left by the closure of the Tethys Ocean. It is the longest and most complex mountain building event of the Cenozoic era, and it is still ongoing. Within these mountain belts, if you know where to look, you can find direct physical evidence of the Tethys ocean floor, ophiolites. These are fragments of ancient oceanic crust that were abducted, thrust up onto the continental margin rather than subducted down into the mantle during the collision process. They consist of the characteristic rock sequence of oceanic crust. Pillow basalts at the top formed when lava erupted underwater and chilled rapidly into rounded pillow shapes. Beneath that, sheeted dikes, the frozen remains of the magma conduits that fed the surface eruptions. Then gabbro, the coarse-grained equivalent of basalt that cooled more slowly at depth. And at the base, peridotite, the mantle rock from which the magma originated. Ophiolite sequences in the Alps, in Turkey, in Oman, in Pakistan are slices of former Tethys ocean floor now exposed at the surface. Geologists can walk on rocks that were once several kilometers below the surface of the Tethys, can examine pillow basalts that formed on a mid-ocean ridge in the middle of a vanished ocean 200 million years ago. These ophiolites are windows into the lost ocean, physical remnants of a seafloor that otherwise no longer exists. The Oman ophiolite, known as the Samail ophiolite, is perhaps the most spectacular example. It is the largest and best preserved ophiolite on Earth, covering an area of about 20,000 square kilometers in northern Oman and the United Arab Emirates, exposed by the collision between the Arabian Plate and the Asian margin. Here you can stand on what was once the floor of the Tethys Ocean, look at pillow basalts formed at a Tethyan spreading ridge roughly 90 million years ago, and understand viscerally what it means for a piece of oceanic seafloor to survive the collision process and be preserved at the surface rather than recycled into the mantle. Most of the Tethys seafloor is gone, swallowed by subduction, its material recycled into the mantle and eventually to return in some future volcanic eruption. But the ophiolites are survivors, the fragments that escaped destruction, and they carry with them a record of the lost ocean that could not otherwise be preserved. By 34 million years ago, in the early Oligocene epoch, the Tethys, as a continuous ocean connecting the Atlantic to the Indo-Pacific, was essentially finished. The collision zones had progressed to the point where there was no longer a seaway through which ocean water could flow continuously from west to east. The great circumglobal equatorial current that had characterized the Mesozoic world was broken. The planetary climate engine was shutting down, and the consequences of that shutdown would reshape the climate of the entire planet in ways that are still being felt today. But before we get to the climate story, there's another chapter in the Tethys saga that deserves attention, one that is less well known but equally fascinating. When the main Tethys Ocean closed, it didn't disappear completely overnight. The collision process was complex and uneven, and in some regions, bodies of water persisted long after the main ocean had been consumed. To the north of the main Tethys, in the region that stretched from what is now the Alps through Central Asia, there had been an extension of the Tethys known as the Paratethys, a broad, somewhat separated inland sea that covered much of what is now Eastern Europe and Central Asia. As the Tethys closed and the Alpine and Himalayan collisions progressed, the Paratethys was progressively isolated from the main ocean, cut off by rising mountain chains, becoming increasingly landlocked. The story of the Paratethys is extraordinary in its own right. As it became isolated, it developed its own distinct ecosystem, a world apart from the main ocean. The salinity fluctuated dramatically as connections to the ocean were repeatedly established and then broken again. In times of connection, marine species colonized it. In times of isolation, the water freshened and many marine species went extinct, while freshwater and brackish water species that could tolerate the changing conditions diversified rapidly. The Paratethys became, in a sense, an evolutionary laboratory, a giant isolated body of water where species adapted to unusual and constantly changing conditions. Many of the endemic species that evolved in the Paratethys have no close relatives elsewhere, products of millions of years of isolation and adaptation. And the remnants of the Paratethys, the modern Caspian Sea, the Black Sea, and the much diminished Aral Sea, still harbor relics of this ancient isolated ecosystem. The Caspian seal, found nowhere else on Earth, the unique sturgeon species of the Caspian, the peculiar fauna of the Black Sea's deep anoxic waters, These are the biological descendants of paratethyan life, survivors from an inland sea that was itself a survivor of the Tethys. The Mediterranean story is different, and here is another twist that surprises most people when they first encounter it. Despite appearances, despite the fact that the Mediterranean sits in roughly the right geographic position, despite the fact that Mediterranean fossils show clear Tethyan affinities, the modern Mediterranean Sea is not the Tethys. It is not a remnant or a relic of the Tethys in the way that the Caspian is a remnant of the Paratethys. The Mediterranean is, geologically speaking, a much younger and more complicated body of water, connected to and largely created by the opening of the Atlantic, rather than being a surviving fragment of the ancient Tethys. The Western Mediterranean, in particular, opened as a series of rift basins in the Oligocene and Miocene, driven by the same Atlantic opening forces that were pushing Africa against Europe. The connection between the Atlantic and the Mediterranean, and between the Mediterranean and the Indo-Pacific, has opened and closed multiple times over the past 30 million years as the collision between Africa and Europe progressed in fits and starts. And that connection history leads to one of the most dramatic events in the Tethys story's aftermath, an event so extreme, so geologically spectacular, that when it was first proposed in the 1970s by the geologist Kenneth Shue and his colleagues drilling in the Mediterranean, it was met with widespread disbelief. The event is called the Messinian Salinity Crisis, and it occurred between 5.96 and 5.33 million years ago, a period of less than a million years in the Miocene epoch. What happened was this. The connection between the Atlantic Ocean and the Mediterranean Sea was severed by the collision between Africa and Europe. The strait or straits that had previously allowed Atlantic water to flow into the Mediterranean were closed by tectonic uplift, by mountain building, by the progressive closure of the seaway that is now represented by the land of Morocco, Algeria, and Spain. And when those connections closed, the Mediterranean began to evaporate. The Mediterranean has no net inflow from rivers sufficient to balance its evaporation rate. It loses more water to evaporation than it gains from rainfall and river input. Today, this deficit is made up by water flowing in from the Atlantic through the Strait of Gibraltar. Take away that Atlantic inflow, and the Mediterranean begins to shrink, and shrink, and shrink. Models and geological evidence suggest that within a few thousand years of the connection being severed, the Mediterranean had dropped dramatically. Within tens of thousands of years, it may have dropped hundreds of meters below global sea level. And if the isolation persisted long enough, significant portions of the basin may have evaporated almost completely, leaving behind in the deepest parts of the basin thick deposits of evaporate minerals, gypsum, anhydrite, halite, the minerals that form when seawater evaporates. And that is exactly what the drilling revealed. Beneath the floor of the modern Mediterranean, in many areas, there are enormous deposits of evaporate minerals, salt and gypsum sequences that in some places are 3 to 4 kilometers thick. The material of an evaporated sea, preserved beneath the sediment that accumulated when the ocean returned. The Nile River during this period carved a canyon that dwarfed the modern Grand Canyon, cutting down to the dramatically lowered sea level, a canyon that can be traced in seismic data far out into what is now the Mediterranean seafloor, before it was buried by sediment when the basin refilled. The refilling event, called the Zanclean Flood, which occurred approximately 5.33 million years ago, may have been one of the most spectacular events in the recent geological record. When the Atlantic connection was re-established, perhaps through the breaching of a rock barrier by the rising Atlantic, water began pouring into the almost empty Mediterranean basin. The geometry of the situation, a vast basin sitting hundreds of meters below sea level, connected to the Atlantic by a relatively narrow channel, would have created conditions for a flood of almost incomprehensible scale. A waterfall or rapid many times the volume of any modern river, filling the basin over a period that may have been anywhere from a few years to a few thousand years, geologically instantaneous in either case. The Mediterranean, as we know it today, a sea full of water and life, is the result of this refilling event. The Zagros flood is perhaps the closest geological analogue to the great flood stories that appear in many human cultures, though it predates any possible human observation by millions of years. Now we need to turn to the question of what the death of the Tethys meant for Earth's climate, because this is where the story becomes truly global in its implications, where a regional geological event turns out to have planetary consequences that are still unfolding today. The Tethys, as we have established, was a climate machine. Its warm equatorial waters drove global circulation, maintained the Mesozoic greenhouse, kept the planet in a warm, equable state for 200 million years. As long as the circumglobal equatorial current could flow, as long as Tethyan waters could circulate around the globe, the planet stayed warm. But as the Tethys closed, that circulation was progressively disrupted. The seaway narrowed, then was broken into isolated basins, then closed entirely. The warm equatorial current was cut off, and the planet began to cool. This cooling was not the only climatic consequence of the Tethys closure. The mountains that rose from the collision zones, particularly the Himalayas and the Tibetan Plateau, were themselves powerful climate-forcing mechanisms. High mountains enhance rainfall on their windward sides, creating intense chemical weathering of exposed rock, and chemical weathering of silicate rocks consumes carbon dioxide from the atmosphere, drawing it down, reducing the greenhouse effect, cooling the climate. The Himalayan uplift, driven by the India-Asia collision, the collision that closed the Tethys and built the mountains from its remains, accelerated silicate weathering on an enormous scale. The Ganges and Brahmaputra rivers, draining the Himalayas, carry extraordinary quantities of dissolved minerals to the ocean, the products of intense chemical weathering. Over millions of years, this weathering has drawn down atmospheric CO2 significantly, contributing to the long-term cooling trend of the Cenozoic era. The Tethys, by dying and producing the Himalayas, set in motion a climate feedback that has been cooling the planet ever since. But there was another, equally important mechanism. The closure of the Tethys, combined with the drift of Antarctica to its polar position and the progressive isolation of the Southern Ocean, eventually allowed the formation of the Antarctic circumpolar current, a continuous flow of cold water circling Antarctica with no continental barrier to interrupt it. This current thermally isolated Antarctica, preventing warm subtropical water from reaching it and allowing Antarctic ice sheets to form and persist. The first permanent Antarctic ice sheet appeared approximately 34 million years ago at the Eocene-Oligocene boundary, and its formation marks the beginning of the modern icehouse world. The transition from the Mesozoic greenhouse to the Cenozoic icehouse that has characterized the last 34 million years of Earth's history, and that ultimately produced the ice ages of the Pleistocene and the climate system that Homo sapiens evolved within. The closing of the Tethys did not cause this transition by itself, but it was an essential part of the reconfiguration of ocean circulation that made it possible. And there is one more climatic legacy of the Tethys closure that deserves emphasis because it affects the lives of billions of people today: the Asian monsoon. The great seasonal reversal of winds and precipitation that brings life-giving rainfall to South Asia, Southeast Asia, and East Asia, that fills the rivers of India and Bangladesh and China, that makes possible the agriculture that feeds more than half the world's population, is in significant part a product of the Himalayan uplift that resulted from the closure of the Tethys. The Himalayas and the Tibetan Plateau act as an enormous thermal and mechanical barrier. In summer, the plateau heats up more rapidly than the Indian Ocean, creating a powerful low-pressure system that draws moist ocean air northward and inland, producing the monsoon rains. Without the Himalayan uplift, without the Tibetan Plateau at its extraordinary elevation, the Asian monsoon as we know it would not exist. The rain that falls on the Ganges plain, the water that flows in the Mekong and the Yangtze and the Irrawaddy, the seasonal floods that have shaped Asian civilization for thousands of years. All of this is downstream, literally and figuratively, from the death of the Tethys Ocean. The lost ocean, by producing the mountains that replaced it, created the climate system that sustains the largest human populations on Earth. The Tethys also shaped the distribution of life in ways that are still visible in modern biogeography, the study of where species are found and why. The Tethys acted for much of its existence as both a barrier and a highway. As a barrier, it separated the northern and southern continents, preventing land animals from moving between Laurasia and Gondwana, except where island chains or land bridges occasionally provided stepping stones. This separation drove evolutionary divergence, allowing lineages that were separated by the Tethys to evolve independently for millions of years, producing the distinct faunas of the northern and southern land masses. As a highway, it provided a route for marine organisms and for dispersal events where animals crossed the water, connecting biotas that would otherwise have remained separate. The closure of the Tethys was a biogeographic event of the first order. When the seaway finally closed and land connections were established between Africa and Eurasia, and when the marine connection between the Atlantic and the Indo-Pacific was severed, previously separated biotas came into contact, or previously connected ones were separated. The great faunal exchanges that occurred as Africa and Eurasia became connected, the movement of proboscideans, ancestral elephants and their relatives, northward from Africa into Eurasia, the movement of horses and deer and bovids southward from Eurasia into Africa. These exchanges happened across the land that replaced the Tethys, through the very mountain ranges and plateaus that had been built from Tethyan seafloor. And the separation of the Atlantic and Indo-Pacific marine faunas, which had been connected through the Tethys, set in motion a divergence of previously related marine lineages that continues today. Many pairs of closely related species in the Atlantic and Indo-Pacific, species that clearly share a common ancestor but have been separated long enough to become distinct, trace their separation to the closure of the Tethyan Seaway. There is even a connection though it requires following several steps of reasoning between the Tethys closure and the evolution of our own lineage. The emergence of grasslands in Africa and Eurasia during the Miocene and Pliocene, a major environmental shift that created the savanna habitats in which early hominins evolved, was in part driven by the climate changes associated with Himalayan uplift and the cooling and drying of continental interiors that resulted from the reconfiguration of atmospheric and oceanic circulation following the Tethys closure. The specific environments that shaped human evolution, the open grasslands of East Africa, where Australopithecus and early Homo walked upright and developed stone tools, existed in part because of climate changes that cascaded from the death of an ocean millions of years before the first hominin appeared. The Tethys is in our evolutionary history, distantly but genuinely, another thread in the extraordinary web of consequences that flows from this vanished body of water. And yet, for all its influence, the Tethys is almost invisible in everyday consciousness. Most people have never heard the name. The mountains it built are famous, the oil it produced is ubiquitous, the climate system it helped create is the one we live within. But the ocean itself, the source of all these consequences, is unknown to all but specialists. It exists in the geological literature, in the fossil record, in the rocks of every mountain range from Morocco to Myanmar, but not in common knowledge, not in the way that more recent geological events, the ice ages, the eruption of Vesuvius, the formation of the Grand Canyon, have entered popular awareness. Part of the reason is the timescale. 250 million years is genuinely difficult to grasp. The human mind is not equipped to feel the difference between 1,000,000 years and 100 million years in any meaningful way. Both are simply vast, beyond intuition, beyond visceral comprehension. And yet, the Tethys operated on exactly these timescales, living and dying over intervals that dwarf the entire history of multicellular life, as most people understand it. The ocean existed for longer than the difference in age between the dinosaur-killing asteroid impact and the present day. It is ancient in a way that resists easy comparison. But the fossils on Everest bring it into focus. Those ammonites and brachiopods, those creatures that lived in a warm, shallow sea and sank to the bottom and were buried in carbonate sediment and were eventually lifted 29,000 feet into the air by the collision of continents, they are tangible. They are real. You can hold them in your hand if you happen to be at the right altitude on the right mountain. And they say, with more eloquence than any abstract geological argument, that the world is not fixed, that what seems permanent is temporary, that the highest places were once the deepest, that the most stable-seeming features of Earth's geography, the mountains, the ocean basins, the distribution of land and sea, are in constant motion, always have been, always will be. The Tethys is gone, but its consequences are not. They are in the mountains you see on a clear day. They are in the fuel in your car. They are in the rain that falls on the fields that grow your food. They are in the air you breathe, shaped by the carbon cycle that the Tethys helped establish, and that the Himalayas, its tombstone, have been modulating ever since. They are even, in a roundabout way, in your own evolutionary history, in the series of environmental changes that produced the ancestors who produced you. The lost ocean is the most present absence in the natural world. There is one more dimension of the Tethys story that deserves its own space, its own careful examination, because it connects the ancient ocean to questions that feel urgently contemporary. We have talked about what the Tethys left behind in rock and fossil and mountain. We have talked about the oil fields and the climate shifts and the monsoons. But there is a subtler legacy, one that operates at the level of chemistry and atmosphere, and it concerns the carbon cycle in ways that speak directly to the world we are navigating right now. The Tethys Ocean was, for most of its existence, an extraordinarily productive biological system. Its warm, shallow margins teemed with photosynthetic organisms, phytoplankton and algae, and reef-building creatures that fixed carbon from the atmosphere and built their bodies from it. And when these organisms died, a fraction of their organic material sank to the sea floor and was buried, removed from the carbon cycle, locked into the sediment. This biological carbon pump, operating continuously across the vast surface area of the Tethys for 200 million years, sequestered an enormous quantity of carbon. Some of it became the oil and gas we have already discussed. But much more of it was incorporated into carbonate rocks, into the limestone and dolomite of the Tethyan margins, carbon taken from the atmosphere as CO2, incorporated into shells and skeletons, and eventually lithified into rock. The Tethys was one of the great carbon sinks of geological history, and its operation over 200 million years was one of the factors that kept atmospheric CO2 at the levels that characterized the Mesozoic, levels that were higher than today, but not runaway, maintained in a long equilibrium by the balance between volcanic outgassing and biological and chemical sequestration. When the Tethys closed, that enormous carbonate factory largely shut down. The shallow tropical margins where limestone had accumulated for hundreds of millions of years were lifted into mountains, removed from the marine environment, exposed to weathering. The weathering of those ancient Tethyan carbonates, the dissolution of limestone in rain acidified by CO2, actually releases carbon back into the atmosphere over geological timescales. At the same time, the silicate weathering of the Himalayas, the weathering of the non-carbonate rocks thrust up by the India-Asia collision, was drawing CO2 down. These two opposing carbon cycle effects, carbonate weathering releasing carbon and silicate weathering consuming it, have been operating in complex interplay ever since the Tethys closed, and their net effect has been one of the factors driving the long-term cooling of the Cenozoic climate. The carbon that the Tethys locked up over 200 million years has been slowly released and re-released, shuffled between ocean and atmosphere and rock in a cycle that operates on million-year timescales, but has shaped the climate background against which all of recent Earth history, including human history, has unfolded. Now consider what we are doing with the carbon that the Tethys sequestered as oil and gas. In the span of roughly 2 centuries, we have extracted and burned a significant fraction of the hydrocarbon reserves that took the Tethys millions of years to accumulate. The carbon that was removed from the atmosphere by Tethyan plankton over geological time is being returned to the atmosphere in what is, by any geological standard, an instantaneous pulse. The Tethys spent 200 million years helping to regulate atmospheric carbon. We are undoing a substantial portion of that work in a few hundred years. The irony is almost architectural in its precision. The ocean, whose closure helped cool the planet, is now, through the hydrocarbons it left behind, contributing to warming it. The Tethys gave us both the problem and in the mountains it built and the carbon cycle those mountains drive, part of the long-term geological solution. Though the geological solution operates on timescales of millions of years, while the problem operates on timescales of decades. But let us step back from the immediate and return to the geological, because there are aspects of the Tethys story that have not yet received their full due. One of the most fascinating is the question of what the Tethys tells us about the deep structure of Earth's Wilson cycle, the recurring process by which supercontinents assemble, break apart, and reassemble over periods of roughly 500 million years. The Wilson cycle, named after the Canadian geophysicist Tuzo Wilson, who first described the systematic opening and closing of ocean basins in the 1960s, is one of the fundamental rhythms of plate tectonics, and the Tethys is one of its clearest expressions. The cycle works like this. A supercontinent sits atop the mantle. The mantle beneath it heats up, unable to lose heat efficiently through the insulating blanket of continental crust. Hotspots develop, rifts form, the supercontinent breaks apart. New ocean basins open in the rifts, growing over hundreds of millions of years as seafloor spreads outward from the central ridge. But the oceanic crust being created is continuously cooling, contracting, becoming denser. Eventually, it becomes dense enough to sink back into the mantle through subduction. The subducting ocean floor pulls the attached oceanic plate behind it, and the continents on either side of the ocean are drawn toward each other. The ocean closes. The continents collide, build mountains from the compressed oceanic remains, and a new supercontinent forms. And then, the cycle begins again. The whole process takes approximately 400 to 500 million years for a complete cycle, though individual components vary enormously. The Tethys fits into this framework as one of the great Tethyan-type oceans, an ocean that formed when Gondwana began breaking apart, grew for 200 million years, and then closed as its margins were consumed by subduction and continental collision. Its opening was driven by the same mantle processes that drive all ocean formation. Its closing was driven by the same subduction dynamics that have closed countless ocean basins throughout Earth's history. It is, in this sense, not unique. It is one instance of a recurring pattern, one iteration of the Wilson cycle, one chapter in a story that has been repeating since Earth first developed plate tectonics, perhaps 3 billion years ago. What makes the Tethys unusual, what elevates it above just another ancient ocean in the geological record, is the quality of the evidence it left behind and the directness of its connection to the modern world. The Alps and Himalayas are not ancient eroded stubs like the Appalachians or the Scottish Highlands, evidence of collisions so old that the mountains have been worn nearly flat by erosion. They are geologically young, geologically fresh, still rising, still being actively shaped by the ongoing collision of plates. The collision that closed the Tethys is not finished. India is still moving north. Africa is still pressing against Europe. The Zagros fold and thrust belt in Iran is still being compressed. Earthquakes in the Himalayas, in Turkey, in Iran, in Greece, in Italy are all expressions of the ongoing closure of the last remnants of the Tethyan domain. The Tethys is still dying, slowly by geological standards, and we feel the tremors of its dying in the seismic activity that periodically devastates communities across the alpine Himalayan belt. This is a sobering thought. The earthquakes that struck Turkey and Syria in February of 2023, killing more than 50,000 people, occurred along a fault system in the complex collision zone, where the Arabian Plate, formerly part of Africa, is being pushed northward into Eurasia, a movement that is part of the same grand tectonic story as the closure of the Tethys. The people who died in those earthquakes died in a very real geological sense because the Tethys has not yet finished closing. The energy released in those earthquakes was the energy of plate convergence, of continental collision, of the same process that built the Alps and the Himalayas and the Zagros. The lost ocean is still making itself felt, not just in the fossil record and in oil fields and in climate patterns, but in the ground shaking beneath living people. The Tethys is not entirely the past. Its consequences are present, active, ongoing. There is something in this that demands a kind of geological humility. We tend to think of the landscape as fixed, as background, as the stable stage on which human events play out. The mountains are simply there, have always been there, will always be there. The earthquake that strikes occasionally is an aberration, a departure from the normal stillness of the ground. But the geological perspective inverts this entirely. The mountains are temporary in the process of being built and eventually worn away. The earthquakes are not aberrations, but the normal expression of the forces that build the mountains. The landscape is not fixed, but fluid, moving on timescales that dwarf human experience, but are as real and continuous as any other physical process. The Tethys reminds us of this. It was a vast ocean for 200 million years, and now it is mountains and oil fields and salt deposits and landlocked seas. What seems permanent is always in transition. The permanence is an illusion produced by the shortness of a human lifetime relative to the slowness of geological change. And yet the Tethys also offers something like comfort, if you are willing to accept comfort on geological terms. The closing of the Tethys, catastrophic as it was for the organisms that lived in it, and for the climate patterns it had maintained, was not the end of anything fundamental. Life continued. It adapted. The organisms that lost their warm Tethyan habitat evolved and diversified in the new, cooler, more complex ocean circulation that replaced it. The mountains that rose from the Tethys's remains created new habitats, new ecological niches, drove new evolutionary radiations. The climate that cooled as the Tethys closed was not a worse climate for life in general, just different, and eventually it produced the ice ages that carved the landscapes of the Northern Hemisphere and the climatic conditions in which our own species evolved. Disruption and transformation are not the same as destruction. The Tethys was disrupted, transformed, and in its transformation, it became something new, something that the ocean itself could never have become, something that now includes us. The fossils on Everest are not a tragedy. They are a testament. They testify that this rock was once seafloor, that this seafloor was once teeming with life, that this life was buried and preserved and eventually lifted to the highest point on Earth. They testify that the planet is alive in the deepest sense, not just biologically, but geologically, that its surface is in constant motion, that nothing we see is final, that every mountain will eventually be an ocean, and every ocean will eventually be a mountain. They testify that the forces shaping the world operate on timescales so vast that any individual lifetime, any civilization, any species is but a brief guest on a planet that was ancient before we arrived and will continue long after we are gone. But brief guests can still pay attention, can still learn to read the record written in the rocks, can still stand on a summit at 29,000 feet and recognize that they are standing on a former seafloor, that the creatures whose remains are in the stone beneath their feet lived in a warm tropical ocean before any mammal had evolved, before any flower had bloomed, before any grass had covered any plain. Can still feel, if only dimly and intellectually, the strangeness and the grandeur of a planet that has been running its geological engines for 4.5 billion years and shows no sign of stopping. The Tethys Sea. It existed for 250 million years, longer than the time that separates us from the first dinosaurs. It was warm, shallow, biologically extraordinary, climatically powerful, a machine for making limestone and oil and climate and life. It was consumed, plate by plate and million year by million year, by the same forces that had created it. Its floor dragged into the mantle, its sediments scraped off and plastered against colliding continents, its margins crumpled into the highest mountains on Earth. It left behind the oil that fuels the modern economy, the mountains that create the monsoons that feed billions, the climate feedback that helped cool the planet into the icehouse world we inhabit, the seismic hazard that threatens millions of people across the alpine Himalayan belt, the landlocked seas that carry the biological echoes of its isolated waters, and the fossils on Everest that started this whole story. It was lost, and it was never truly gone. And now that you know it was there, you will never look at a mountain quite the same way again. And here is perhaps the most remarkable thing of all. The Tethys may not be entirely without a successor. Look at the Red Sea. It is a young, narrow body of water, only about 20 million years old, formed by the rifting of the African and Arabian plates. It is widening at roughly 1 to 2 centimeters per year, which is slow by human standards, but swift by geological ones. In 50 million years, if the rifting continues at its current rate, the Red Sea will be a substantial ocean. New seafloor is forming at its center. The process that began with the Tethys, the cycle of ocean opening and closing that has characterized Earth's surface for billions of years, continues. The Red Sea is an embryonic ocean, just as the Tethys once was. Whether it will grow to rival the Tethys in size and influence, whether it will produce its own mountain ranges and oil fields and climate consequences when it eventually closes, is a question for geologists tens of millions of years from now to answer. Earth doesn't lose oceans permanently. It transforms them. It closes them and builds mountains from their remains. It buries their sediments and cooks them into oil. It uses their closures to redirect climate systems and drive evolutionary change. And then it opens new ones, begins the cycle again. The Tethys was one iteration of a process that has been running since Earth first had liquid water on its surface, a process that will continue long after the Red Sea has grown old and the next generation of mountains has risen from its closing. We are, all of us, living in the aftermath of the Tethys, on a planet shaped by an ocean we never knew but have always depended on. The seashells on Everest are not a puzzle. They are an answer. They tell us that this world is older and stranger and more dynamic than it appears, that the ground beneath our feet has been ocean floor, that the mountains on the horizon were once tropical seabeds, that the oil in the engine, was once the body of a marine organism floating in a warm equatorial sea. That the rain falling outside was shaped by mountains built from the crushed remains of a vanished ocean. Everything connects. Everything has history. And sometimes, if you climb high enough, you can hold that history in your hand. The Tethys Sea, the lost ocean. It was here for 250 million years, shaped the world in ways we are still discovering, and left so many fingerprints on the present that once you start looking for them, you find them everywhere. In the mountains, in the fuel, in the rain, in the fossils, at the top of the world. It was lost, but it was never truly gone.